So this chapter has got a few concepts. I hope you grasped all of them, especially about defining instabilities, potential temperature, moist potential temperature, convection, and so on. We will not specifically come back to convection in the rest of the course. We will go into dynamics of the ocean and the atmosphere, but we will use the ideas of potential temperature, moist processes, parcels, energy transport, and so on. Okay, so the exposure to convection is good because it is an important part of the energy transport, which is part of the large-scale climate dynamics. It's the fundamental driver of climate and weather, right? We'll see that. The energy balance we did not look at the equator to pole temperature gradient, but we will see in the next chapter the meridional structure of the atmosphere and the ocean, and we'll see that that will require that we move energy from low latitudes to high latitudes, and convection is a big part of that. So in that context then, where does convection actually occur in the real world? So the best way to do that is to look at this map of so-called outgoing long-wave radiation. We saw this as a part of the energy balance, sorry about that, where we said shortwave comes in, does a bunch of things, and then planet tries to lose energy as long-wave. Clearly separated spectra of the shortwave and the planet's outgoing long wave. With love and affection, it is typically referred to as OLR, outgoing long wave radiation. So if you say OLR in a group, they probably think you're an expert, so you can use that freely. Obviously, it's a flux in watts per meter squared. What do you have to remember? Basically, the OLR is going to depend on the emission temperature. Remember sigma T to the fourth? We kept saying sigma TE to the fourth, right? So TE is the emission temperature. And what does convection do? It raises the water, the parcel, condenses the air, the moisture in it, which produces heat, produces buoyancy, further raises the parcel, and so on, and drives all the way to the top of the atmosphere in the cumulonimbus, as we saw, and that actually cools the top of the cloud. So cloud tops actually emit at a lower temperature when they are deep convecting clouds. Which means what? Which means the regions of convection show up as relative minima of OLR, right? So this map should immediately make sense if you have been exposed to the structure of the atmosphere before. We haven't explicitly seen this, even though we saw the subtropical high, right? So we mentioned Hadley cell. There is rising air in the intertropical convergence zone, which hits the ceiling, the tropopause, goes poleward in the Hadley cell and sinks over the subtropical highs. So here you get high OLR. So here it is a value of 260 or so, and you can see similar values over here in the desert. So wherever there is sinking motion, as we said, compression, adiabatic warming, but there is radiative loss, so the buoyancy doesn't increase and the air doesn't go back up, so there is a slow sinking. That much we learned. And this belt of low OLR in the tropics and a real huge region of low OLR over the West Pacific, Indonesia, and so on, and here and over the rainforests of Amazon, Central Africa, in the warmer side of the Indian Ocean. So this is a continuum from West Pacific, Indonesia into the Indian Ocean and so on. So it's funny that the tropics are warm. That's where convection happens. So you need warm air for convection. You need warm surface to drive the rising air and moisture. And yet you are emitting at low temperatures in the tropics in these regions because the cloud tops are cold. whereas where there is no rain and it's not that hot, the OLR is high, so you are emitting to space at a higher temperature. Okay, if there is no cloud, obviously surface can reach all the way to the space, like it does on deserts, for example. So wherever the Hadley cell comes down, obviously there are deserts. So these are deserts of the ocean, as I mentioned before. We'll see that in ocean color, ocean productivity later on. And these are land deserts. India should be desert, but it's only desert in the northwestern part because of the monsoonal circulation we get here. And there is other reasons why OLR is low here. You can have glaciers and snow and so on. So at the polar latitudes, obviously, temperatures are much cooler, so OLR drops off. Okay, so this contrast is very interesting to note. So warm surface is needed for convection, but as the air is lifted and convected up in the process of rising air, condensation, heating, and further rising and so on, hitting the cloud top here, creating anvil, etc. You get colder temperatures at the cloud top. Sigma Tc to the fourth is lower than where the ground can directly emit at the surface temperature, which is always warmer than the atmospheric temperature. Okay, on the ocean you get some places where the sea surface temperature can be warmer than the atmosphere, and that takes some special processes to happen. But in general, this is what happens. That's why you get this kind of OLR distribution. So long story short, this is where the convection happens in the tropics. There are convection happening at higher latitudes that are intermittent, that are not persistent, like in the ITCZ and so on, where there is year-long convergence, rising motion, clouds, and rain. The story can be concluded by looking at what we said before. These are just problems in the book. I won't go through them, but you can look at that. As I said later on at the end of the course, maybe I'll go through one typical problem from each chapter and show how the solutions work. So this actually concludes this chapter on convection. It's a few interesting concepts, and I hope you got all of them and that you keep them, because we will need most of them again with dynamics. So here you should be able to look at the equations and not be uncomfortable, even if you don't derive them. If you're not able to derive them from scratch, you should be able to go through them, explain the steps as to what the derivation is leading up to and how we actually get things that we derived, whether it's simple lapse rates or potential temperatures, moist processes, and so on. So get very comfortable with the equations. That is actually very important for any dynamics course. Okay? Because we'll get more and more equations as we go along, and we will make more and more assumptions and derive many things. So equations, equations, equations. Get comfortable.